out and
Ms. Sharma?
okay, guys, so let's do it now. So we are finishing off this chapter 9 with the gases, and we already covered 9.5 and 9.6 earlier, which was we are not going to go all these, these problems which relate to the non-ideal gas behavior and the kinetic molecule. I mean, we're not going that far. So we just did a brief introduction of kinetic molecular theory. So 9.5 and 9.6 was discussed earlier, right? When we did the first introduction to the gases in that. But the problems that are in 9.5 and 9.6, leave out, do not do them. So we talked about the ideal behavior, non-ideal behavior, all this entire kinetic. That's one thing. And second thing is you are also going to leave out this problem, which is, I mean, you can try on your own if you want to. So leave out the problem 9.21. Okay, so that's like, that relates to effusion and diffusion. But now we are going to do the density, and that's the formula. You should make the note of these formulas. They are not given in your handout. And last time I made you write these formulas. So once again, it's a continuous process. Then we are going to do the calculations that relate to the molar masses, right? How to get the molar mass of a gas. And what's the formula for that one? Make a note of it. Then obviously, we have already done the empirical formulas and found the formula mass the molecular formula based off of the empirical formula. But today we're going to look at how it applies to the gases. How do you find the molecular formula of a gas? Then this is Dalton's law of partial pressure. Okay, Dalton's law of partial pressure. And so Dalton's law of partial pressure, we're going to look at, basically the Dalton's law is this: total pressure of the gases is equal to the sum total of the partial pressure of each of the gases that comprise that mixture. But these partial pressures, how do you get them? So the partial pressure of the gas is also, you can get it from the mole fractions. Okay, the total moles, if you know the total moles, if you know the partial moles of every gas, then you can find the mole fraction and so forth. So these formulas, again, write these down. Then we are going to do the collection of gases over the water. That's the downward displacement. This is called downward displacement of water. Displacement of water. And then this is Graham's law. Graham's law is the last one, Graham's law. And that relates to the speed at which the gases move. So this is the rate of effusion, rate at which they move, right? They diffuse in the air, the speed. So that is obviously the manifestation of their masses or the molar masses. So the heavier gases will move faster, they will move slower. The lighter gases are going to move fast. So that's thing. So let's do these calculations. There are roughly about 10 to 11 problems that I plan to cover. And that's what it is. So, all right. So first is the measuring the density. That is the problems in the learning check. So I'm going to all do learning check and learning check problems, because they're not done for you. So those that we cover in the lectures. And the ones that are done for you are the ones that go for your, extra credits. Anyway, so here's the learning check, and I'll just put this in LC problems. And so the very first one is 9.11 learning check. And that is, let's put this LCK, CK. Okay, now. Learning check, page 481. And now, so this is a different book. I mean, I have a other softer version. So anyway, so you get it, 9.11. So here we are doing measuring the density of a gas, measuring the density. So How do you measure the density? So density, first of all, the formula for that is the molar mass times the pressure of the gas divided by the gas constant times T. Okay, so M stands for the molar mass. P stands for the pressure the gas is exerting, right? R stands for the gas constant, and it has a value here. And then T is the temperature. Now, temperature will be in Kelvin. So whatever you get in Celsius, you convert that to Kelvin. The value of the gas constant is 0.082, 01. 1 minute. So 0.08201 liters atmosphere per mole K. Now, here's the thing. Your book is also giving you 0.0821. So this is also okay. You know that it doesn't matter. It's just a little, difference, but 0.08201 is more exact. That's the only difference. Okay, so what is given to us here? What is the density of molecular hydrogen? So we are looking at hydrogen gas at 17 degrees Celsius. So we are given the temperature 17 degrees. So 17 plus 273. So let's do this. 273 plus 17. It becomes what? 10, 7, 8, 9, and 2. So 290 K. So that temperature given is plus 273 is equal to 290 K. Next is the pressure given is, so this is the temperature, and pressure is 760 torr. 760 torr. Now keep this in mind that you are given the torr, but here is the ATM. So if you have a torr, you need to convert to ATM. Torr needs to be converted to ATM. And so we have 1 ATM is equal to, torr needs to convert to ATM. We have 1 ATM is equal to 760 torr. So when you are given here, this is saying 760 torr, the pressure, that means that is equal to 1 ATM. So the pressure actually is, pressure in this case is 1 ATM. Okay, 1 ATM. Okay, now what is the density? The rest is you're going to just put it. So density, write down the formula always. Density is the molar mass. So the molar mass for hydrogen is 2 hydrogens times 1 of each is 2 grams per mole. So molar mass, M is always capital. Okay, so just there's a certain way this M is also made. Okay, so like more like italics. Okay, so times the pressure. The pressure is so pressure is 1 over R and T. So 2 grams per mole, okay, times the pressure is 1 ATM over R is 0.08201 liters atmosphere per mole K times 290 K. Okay, so this cancels out the K and K, mole and mole, ATM and ATM, and what you're left with is grams and liters. That is the unit for density. So do the math now. Do the math, which is equal to the density is equal to 2 times 1 divided by 0.08201 times 290. Okay, and so this should be equal to, yes, 0.0, very good. 847 or 84. So this is 0.084. Now, you know, just like even if we go by the units, the what do you call the significant figures, 3 significant figures here, 4 significant figures here. These guys, the ones that are this one and this one, doesn't even apply. So your answer should be in 3 significant figures. So these are 4 significant figures. These are 3 significant figures. So the answer should be in 3 significant figures. That is why you need to bring 47 grams per liters. That's the always write the units and always show the specifics, you know, and those things. Okay. Now let's move on to the next one, which is 8.12. 8.12 is this is 1, 2, 8.12 learning check. Okay, so here we are given acetylene is a fuel used, acetylene, a fuel used welding torches, is composed of 92.3% carbon, 92.3% carbon, and 7.7% is hydrogen by mass, right? So when they say this by mass, with this, that means this is equal to 92.3 grams of carbon and 7.7 grams of hydrogen. Find the empirical formula. So first thing is you need to find the empirical formula. Okay, next is if 1.10 gram of acetylene. Second is that if you are given 1.10 grams of acetylene, which is the name of a gas, occupies a volume. So that is equal to the small m, okay, mass. So small m is equal to mass. And here it is occupying a volume, and the volume is equal to 1.0 liters. Okay, at 1.15 atm, and atm is the pressure. Okay, pressure, and the temperature given is 59.5 degrees Celsius. And you know it that you will have to add 273 to it, to 273.15, it's fine. So you add it, so this becomes 5, 9, 10, 11, 12. This becomes 8, 9, 10, 11, 12, 13, and 3. So 332 Kelvin is the temperature. Okay. What is the molecular formula for acetylene? So the second one is saying find the molecular formula. So we know that some of the relationships, once you get the empirical formula, so empirical formula times N is equal to molecular formula. But how would you find the empirical formula? You're going to first find the empirical formula, then comes the molar mass over the empirical formula mass is equal to N. Okay, so N is that other numerical number. It's not the number of moles, it's just the number. Okay, so let's see. We need to find the so let's see. Okay, so first is you take the do part one. Part one is find empirical formula. So we are given 92.3 grams of carbon. First thing is converted into mole. So 1 mole of carbon over 12 grams of carbon. Okay, you guys do the math. And then the other one is 7.7 grams of hydrogen times 1 mole of hydrogen over hydrogen, just hydrogen 1 gram of hydrogen. So what do you get here? How many moles is that? So we have 92.3 divided by 12, and that is equal to 7.69 moles of carbon. And the other one is 7.7 moles of hydrogen. So it's roughly, you know, the other one is also 7.7. So this also can be made into 7.7. So it's still the same, 7.7 moles of carbon. So you have 1 to 1. So basically 7.7 moles over 7.7 moles that relates to carbon. And then here is the hydrogen again, 7.7 moles and 7.7 moles. So this is 1 to 1. So this is 1 and this is 1. So in other words, the empirical formula is C1H1. Okay, this is the empirical formula. So that's part 1. So that's so next thing is you are going to now find the molecular formula. So molecular, then finding the molecular formula. So how do we do this here? So we have the empirical formula mass, empirical formula mass, find that first. Empirical formula mass is 1 of carbon times 12, 1 of hydrogen times 1, and that gives you 12 and 1, that is 13 grams per mole. Okay, so this is one piece. Next is occupies. Okay, the next is the so next is the molar mass is equal to the mass. So this is what another piece here. The molar mass is equal to mass over the number of moles, okay, or M over N. So you are given this gas is a hydrogen, okay, and we have the mole. So this is also, one second, what was the thing? Gas, this is a hydrogen gas. So no, sorry, it's not, it's acetylene, sorry. So here we have the mass over, one second. I think just give me 1 minute. Okay, so here is the way I'm going to just talk back. So we talked about that for the molar mass, for the molecular formula, we need for molecular formula, you need the, you would need the value of N. Okay, for molecular formula, you need the value of N, and you need also and where do you get this N? This N is different from this N. This N is different. This N is just a numerical number, this one. Okay, so don't worry about this. I don't know, I mean, they could have written something else, but they chose to do that. This is the number of moles. And since acetylene, we don't know the molar mass, because that's what we are trying to determine. The molecular formula will determine the molar mass. So, but we don't know the molar mass. So what we know, what we are given is the mass, which is this. So we are given the mass, We divide that by the number of moles. But how do we get the number of moles? The number of moles you're going to get is from the ideal gas equation. PV is equal to nRT. Okay, so get this. This is the actual moles. Once you get the moles, you divide that by the M, and that's going to give you the mass. Okay, molecular formula or molar mass. Okay, so for molecular formula, we need molar mass, and to find molar mass, we need number of moles, that's N. So we are given the mass in grams, and then we divide that by the number of moles, that's N, and that gives us the molar mass. Okay, so once you get the molar mass, then that's the second step. Once you get the molar mass, you divide that by the empirical formula mass. And this gives you the numerical N, numerical value. And this numerical value is not the moles. So this numerical value, you just take that times N is the molecular formula. Okay, so this is the strategy. Okay, now what we're doing is, find the M is equal to M, small m over the number of N, and N is equal to PV over RT. The given P is 1.15 ATM, 1.15 ATM times the volume is given 1.0 liters. Divide that by R. R is 0.08201 liter atmosphere per mole K. And then the temperature is 332.5 times 332.5 K. Okay. So let's move it a little bit here. Okay. So let's do this calculations. What do you get? So you see that the ATM and ATM cancel out, liter and liter cancel out, K and K cancel out, and you're just left with the unit of moles. So these moles are the one that is this guy. This is this guy. So what do you get here? 1.15 times 1.0 divide by 0.08201 times 332.1. Sorry, 0.5. Okay. 1.15 times 1. So, and then that is 0.08201 times 332.5, and that gives you 31.35. So 1.15 divided by 31.35. 1.15 divided by 31.35, and that is equal to, so that's the value of N is, oh, you guys are getting 0.0421. I'm getting 0.036 moles. Just do this again. 0.0
I think it's your denominator. It should be 27.26.
1 times 332.5 is equal to 27.26. Okay, sorry, my mistake here. 27, this is 27.26. 27.26. Okay, then 1.15 divided by 27.26 is equal to 0.0421. That's correct. Okay, so 0.0421 moles. Okay, now M is equal to the weight. The weight given is 1.10 grams. So take the weight 1.10 grams, divide by the number of moles, that is 0.0421 moles. So that's M over N, and that gives you 1.10 divided by 0.0421 is equal to 26.12. So this is equal to 26.12 grams per mole. Okay, now that's the molar mass. Next thing we are doing is that you take the molar mass and divide by the empirical formula mass. So we already calculated the empirical formula mass, and that is equal to 13. So here is empirical formula mass. Empirical formula mass is equal to 13 grams per mole. So now the numerical N is equal to the molar mass divided by the empirical formula mass. So the molar mass is 26.12 grams per mole. Okay, divide that by the 13, the empirical formula mass, grams per mole. So what does this become? 26.12 divided by 13. And that is 2 point. So this is equal to N. N is equal to 2.009. So anyway, so, you know, it is 2. Now we have, sorry. Now we have the empirical formula times N is equal to molecular formula. In other words, C1H1 times 2 is equal to the molecular formula, and that is equal to C2H2, and that is the formula for acetylene. Okay, all right, guys. Yeah. All right, so next is we are looking at the determining the molar mass of a volatile liquid. All right, any questions so far? Any questions? Anyone?
Record, please.
Any questions anyone has? Okay, yeah, I see Chelsea, thank you, and Anna, thank you. Okay, all right, so next is number 3. Okay, so this is determining the molar mass of a volatile liquid. Now, volatile liquid, what does it mean to you? What do you understand by volatile liquid?
Very reactive.
Volatile, not reactive, but it is volatile means something that evaporates quickly, evaporates quickly, okay? It evaporates quickly. Okay, so we have now, somebody has a message here. So what were we finding? I think yeah, so we were finding what were we finding in the question? What were we finding? So here's the thing. Where was the question? It became a long question. So here we were finding the question is asking you find the empirical formula first. And the next is find the molecular formula. So like in other words, let me put here, find the molecular formula. So that's the thing. But in order to find the molecular formula, you have to go through all this molar mass and all those things. So you got it? Okay, good. Okay, so now we are looking at the volatile liquid. So these acetylene is a gas. Now look at the next is if the liquids evaporate. Okay, the liquids evaporate quickly and they create vapors. And these vapors are also like they're thick, they're like wet, but they are still in the gaseous state. So these vapors are the gases of the liquids that evaporate quickly, and they have their own pressure and so forth. Okay, so there is a certain way these vapors are collected. You can just take these liquids, you can start heating them, and there's a small hole. You let the vapors escape till the last liquid piece is left. Right there you stop, then all the liquid evaporates, but all of it doesn't leave the container. Some of the vapors still remain in the container. Now you are dealing with the vapors of the liquid. So now question is a sample of phosphorus. So this is learning check 9.13. 9.13 learning check. Okay, here you are given a sample of phosphorus. Okay, that weighs 3.243 into 10 to the power minus 2 grams. Exerts a pressure. So this is obviously the value of small m. Exerts a pressure. Now pressure given is 31.89 kilopascals. Okay, kilopascals. In A, the volume given is 56.0 milliliters. So that's the volume. Bulb at the temperature given is 550 degrees Celsius. That's the temperature. Okay. What is the molar mass? So find the molar mass, M, molar mass. Okay. Molar mass and molecular formula. Molecular formula. So find the molar mass and the molecular formula, both the things of phosphorus vapors. Okay, so here are a few things we need to do. We have to do a lot of conversions. First is convert. You are converting the kilopascals to kilopascals to pascals, and then pascals to ATM. So that's first conversion. Next is you're going to convert the temperature, degree Celsius to Kelvin. The third is you're also going to convert milliliters to liters. And with that said, after that, you're going to write the formula. So let's see what the formula is. The molar mass is equal to the molar mass is equal to M, the small m in gram. That's the weight, this piece right here, the grams, times the value of R, which we already know, times the temperature, which is given to us, divide that by the pressure, which is given to us, times the volume. Okay, so that is going to give us the molar mass. And then after that will be the molecular formula. Okay, so let's do this first. Now, we are given, first is what is the relationship of the atmosphere in pascals? So 1 1 kilopascal is equal to 1000 pascals. So first conversion is that. Next is the 1 ATM is 101.325 pascals. 1 ATM is equal to 101.325 pascals. Okay, so let's do this first conversion. That is 3. So pressure from kilopascals to ATM. Let's do this first. 3.243 multiplied by 10 raised to the power minus 2. So, oh, sorry, what am I writing here? I'm writing the mass, sorry. Okay, go back. 31.89 kilopascal times 1000 pascals over 1 kilopascal. All right. And then times ATM also, then 1 ATM over 101.325 pascals. Okay, so we see now that kilopascal and kilopascal cancel out, pascal and pascals, cancel out. So now you just do the math. 31.89 times 1000 times 1 divided by 101.325. All right, do this. What do you get? Yeah, good. So 0.3147. So it's fine. Let's just leave it 0.31 ATM. So that's our pressure value. So this is one piece. Next is we will need to convert the temperature. So 550 degrees Celsius. So the temperature is 550 degrees Celsius. Convert that to Kelvin. So we have 550 degrees Celsius plus 273. And what do you get here? (823 Kelvin. So that's the value of temperature. Next is the volume. So the volume given is 56.0 milliliters. Okay, 56.0 milliliters times 1 liter over 1000 milliliter. And that gives you what? 56 divided by 1000 is 0.056 liters. All right. So we do these conversions. Next is there is a formula in which, so we will get the, what is it called? The molar mass. Molar mass. Okay, molar mass is M. What is that? RT over PV. RT over PV. So put these numbers. The mass is 3.243 times 10 to the power 2. 3.243 times 10 to the power minus 2 grams times 0.08201 grams, liters liters times ATM per mole K times the temperature is 823 K over P, pressure is 0.31 ATM times the volume is 0.056 liters. All right, so this is going to give you the value of molar mass. So do these calculations. What do you get here? .243 times 0.08201 times 823 is equal to 218.88 over 0.31. Okay, 0.31 times 0.056 is equal to 0.017. 0.017. Okay, so 2218.88 divided by 0.017. That is, and that the whole thing is divided by 1000, and you get 12.87. 12.87 grams per mole. Okay, 12.87, 126. How come? Maybe 126, maybe, okay. 3.243 times 0.08201 times 823 is equal to 218.88. Okay, and then times 10 to the power 2. Then 0.31 times 0.056, and that gives you 0.017. Okay, and then there is 10 to the power minus 2. So that means 218.88 divided by 0.017. That gives you 12,875. Divide that by 100. Yes, sorry, 128.7. Okay. So it's not 12, it is coming out to be 128.75, 128.75 grams per mole. Okay, that's what I got. So Chelsea, you're getting 126. What about the rest of you guys over here in the class? What did you guys get? 126 or 128? What about the rest of you guys? I'm going to just pause the video for a minute. Okay, once you get the molar mass, right? The next formula is you take the molar mass. We need to find the value of N because the question is asking us what is the molecular formula. So for the molecular formula, as we talked about earlier, that we would need, you know, the empirical formula, the value of this N, then the empirical formula, the molecular formula will come. But even before that, we need, the actual thing is the molecular, the weight, the molecular weight, right? Or the molecular molar mass divided by the empirical formula mass. Okay, so that's the, like the basics, you know, how these formulas are connected. So we need to find the value of N first of all. So let's do that. N is equal to the mass that is given in grams, and the mass given in grams is for, it's 3.243 into 10 to the power minus 2. So 3.243 into 10 to the power minus 2 grams over the molar mass we just now calculated, which is 128.75 grams per mole. And so this is going to give you the number of moles. So let's do this. So 3.243 divided by 128.75 is equal to 0.025, that's divided by 100. And that is 0.00030 and 251 moles. All right. So we get the value of N like this. Next is we need the empirical formula. Empirical formula, since it's just the phosphorus by itself, and empirical formula is the phosphorus. An empirical formula is the lowest whole number, phosphorus. So phosphorus is just P, and that is just, you know, P1 basically. So what is the formula? What is the weight of phosphorus? So get the molar mass of phosphorus. 31 grams per mole, right? The molar mass of phosphorus is 31. Okay, so now you are taking these just a minute. We got and the molar mass is 128.75. So what are these moles? One second, this is little. Okay, so discard this. This was like, I was overthinking too much. So finding N, in this case, this method of finding N, which is the number of moles, you can discard this. This is not needed. This piece right here. This is not needed. Like I said, I was overthinking on this one. But so just put here, discard this step. But remember that for the molar mass, for the molecular formula, you need the value of N. Okay, and so we need to find N in order to get the molecular formula. So we have the molar mass, which we calculated from top, 128.75, this one. And so use this is the molar mass, divide by the empirical formula. Now here's the thing, in this case, because nothing else is given, what you're given is just the phosphorus. So phosphorus by itself is the empirical formula. So the empirical formula mass for phosphorus would be the molar mass. Empirical formula mass for phosphorus is equal to the molar mass of phosphorus, as you see in the periodic table, molar mass of phosphorus. Okay, so here we see the molar mass of phosphorus is 31 grams per mole. This piece is coming from the periodic table. And this is the one that you calculated from the top. So that gives you 4.4, this is grams per mole. And this bottom one is also grams per mole. Okay, so this gives you this ratio. This is the value of N. So in other words, the empirical formula times N is equal to the molecular formula. So empirical formula for phosphorus times N, which is 4.15, and make it into 4. just 4. So this is equal to P4. And this P4 is the molecular formula of phosphorus. Okay. Sorry for the confusion over here. As best as I'll just remove this, delete this. So you guys don't have it with you. Oh, what happened here? Okay. So any questions so far from this? Any questions, guys? All good? Okay, let's do the next one now. This, I mean, I'll be very honest with you. This was too long. I'm not going to give this thing on the exam. This is like way too much. That's the only thing that I can give is like where, you know, you actually see, I mean, these empirical formula, molecular formula, I find it's so good to know how they got the formulas for the gases, you know, what were the procedures. But this is like, if there's too much calculations involved, I'm not going to, you know, put that in the exam. Anyways, now let's look at the Dalton's law. Dalton's law is of partial pressures. Now, he said that when you take a mixture of gases, okay, you take a mixture of gases, every gas has its own identity. And so it exerts its own very specific pressure, which is very unique to that gas. It depends on the mass of the gas. It depends on, you know, whether it's a molecular gas or it's a atomic gas, or, you know, what is it made up of? What's the weight of that gas? How fast it moves, you know, composition of that gas. So all those things. So every gas is exerting its, you know, pressure on the walls of the container. So that pressure is called the partial pressure. Partial pressure. So what we see outside from a balloon, we only see the total pressure. So this total pressure of all the gases is the sum total of the partial pressure, and partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3 and so forth. Okay, so that as many gases you fill, as many. So the application, it's a very simple law, and just you have to just make sure that the units are the same on all, you know, these pressures. So same units in all, right? That's one thing. Second thing is, if, you know, if they are not the same, then you have to do the conversions. So that's one thing. That's the only thing. The rest is, you know, it's easy. So let's look at this one now. Pressure of a mixture of the gases is, and then also there is a concept of mole fraction. Mole fraction is, you know, the total moles. Mole fraction is the total moles, and then the moles of each gas. So that is expressed as chi. Mole fraction is chi. Chi. Okay, this is called chi or chi of every gas. So if it is gas A, so this is equal to the number of moles of gas A over the total moles. So as many gases there are, you have to calculate the moles of each of these gases. So let's write this down here. Moles of A over the moles that is of all the gases total. All right, so now based on that, this also relates to chi of A. This of, you know, chi of A, or the mole fraction of A, is equal to the partial pressure exerted by A over the total pressure of the gases. So this relates to, this also is related to that. Mole fraction is also related to that. Okay, now let's look at this. Now you are given this problem, learning check 9.14, learning check. Okay, here. Volume given is 5.73 liters, 5.73 liters. It's a flask. At the temperature given is 25 degrees Celsius. 25 degrees Celsius contains, now the number of moles given is 0.0388 moles, 0.0388 moles of, now the gas is nitrogen gas. So this is a good thing, once you have the identity of the gas, then at least you can get a molar mass and, many things. So N is the number of moles of nitrogen, and then the oxygen. So that is, let's just put this here. Wait a minute. Okay, 1 second. For the nitrogen gas, the number of moles of N2 is equal to 0.147 moles. Oh, sorry. No. 0.0388. 0.0388 moles. Next is you're also given carbon monoxide. So the number of moles of carbon monoxide is 0.147 moles. Okay, and you're also given hydrogen. So hydrogen, number of moles of hydrogen is equal to 0.0803 moles. Okay. What is the total pressure? So find P total. So P total pressure. Okay. In a flask, what is the total pressure in the flask in atmosphere? So you need to get this in atmospheres, ATM, that's the unit. Okay. So you are given here the total number of moles, the individual moles, but you can find the total number of moles, combine these. So you get the total number of moles. Okay. And they are saying, what is the total pressure? So same thing, you are going to use, okay. Arshil, what is the total pressure? Okay, so here's the thing, you can also find the partial pressures of each gas, then add, their partial pressures to get total pressure. Okay. All right. Now we are doing this. So let's calculate the partial pressure of hydrogen, partial pressure of nitrogen, and partial pressure of carbon monoxide. How? We have the formula PV is equal to nRT. PV is equal to nRT. Just rearranging this, P is equal to nRT over V. Okay, so here the N for hydrogen is 0.0803 moles times 0.0820, actually it's 0.08206 liters times atmosphere per mole K. And RT, now comes the T. Temperature is, we need to change this, plus 273. 25 plus 273 is what? 8 to 98 K. So times 298 K. This whole thing is divided by the volume, which is 5.73 liters. All right. Next is, you are going to same way you're going to do for the partial pressure for nitrogen. And here we have the moles of nitrogen, 0.0388 moles of nitrogen times the 0.08206 liter atmosphere per mole K times 298 K over 5.73 liters. And then we have the partial pressure of carbon monoxide, which is 0.147 moles times 0.08206 liters atmosphere per mole K times 298 K over 5.73 liters. All right, so get these values. Recording. I don't know, when did I pause the recording? So, okay, I'll just start it by here. The Dalton's law of partial pressure. Okay, so Dalton's law of partial pressure is adding all the partial pressures of individual gases that are inside a container. So from the outside, we only feel the total pressure, but actually it is the individual pressures from each of these gases. So in the learning check 9.14, we have this problem where we are given the number of moles of the three gases, hydrogen, nitrogen, and carbon monoxide, and we are given the volume and the temperature. We need to find the total pressure. So in order to find the total pressure, we need to first find the partial pressure, because this is the formula for the Dalton's law of partial pressure is that partial pressure of one gas, partial pressure of second, partial pressure of third, add together, that gives you the total pressure. So that's what we're doing. You take these, you take the ideal gas law and rearrange. So that gives you that is used to find the partial pressure. So we are given the number of moles, we are given the R value, we convert the temperature from degrees Celsius to K, and then divide that by the volume. In volume has to be in liters. If it's in milliliters, you convert that. So all this, when we convert, we get the partial pressures of hydrogen, nitrogen, and carbon monoxide. And just you add up and you get 1.13, okay? So this is this kind of question, you know, I'm going to just say something like this can be on the test because it is using two gas laws. Okay, so that I'm not going to disclose all that. I haven't even made the test yet, but just to, you know, let you guys know. Okay, let's look at the pressure of the mixture of gases. Okay, the same thing in 9.15, it's the same story, 9.15 learning check. Okay, learning check here is what is the pressure of the mixture of, so you are given 0.200 grams of hydrogen. Okay, all you need to do is here convert to moles. Convert to moles. Okay, so in other words, you can find N. Then you are given 1.00 grams of nitrogen. Okay, and then same thing, convert to moles. Same story is with the argon. You are given 0.820, 0.820 grams of argon. Same thing, convert to moles. So once you have the values of N for hydrogen, you have the value for nitrogen, and you have the value for argon. Okay. Now you are given is the volume, which is equal to 2.00 liters. And you're given the temperature, which is 20 degrees Celsius, plus 273 is equal to 293 K. So you're going to first find the partial pressure. First find the partial pressure of hydrogen, nitrogen, and argon. Same as above. Same as shown above. So I don't have to repeat this. So in other words, the formula you're going to use is P is equal to N R T over V. So once you get the partial pressure of hydrogen plus partial pressure of nitrogen plus partial pressure of argon, and that is going to give you the total pressure. So this thing, you guys can do it because we need to move further. So let's look at now the collection of gases over water. So collection, so this is the lab you actually did, right? Just put there, collection of gases. This is the lab where you collected hydrogen in the oedometer. So same story here, collection of gases, okay, over water. Okay, so how did you get this? Over water. This is, you did this by, your lab, where you took magnesium, you added HCl to it, and that gave you magnesium chloride, which dissolved in the liquid, and hydrogen gas was released. So this hydrogen gas was collected in the oedometer. Okay, so if you remember that, that's how they do this. All right, so that's the oedometer. But other ways are also, like here, for example, you have a reaction going on in a test tube, and in this test tube you are going to put actually a stopper with one hole. So here is a one hole stopper, and in that one hole stopper, what we take is the tubing, okay, which goes from here. This is the one with a very thin pipe, okay, and this pipe bends like this, and then it goes up like that, like this. Okay, so this way, this way, this way, and this way. Okay, so here you have an inverted test tube, also with a hole or something, a one hole or something, like that. And it is placed in a trough. A trough is a container which has a lot of water. So it's placed in a trough. Now, keep this in mind that initially this inverted test tube is filled with water. So this is all filled with water, and this is filled with water till here. And now what happens is that, let us assume that you are trying to get oxygen. So you have KClO3 decomposing. So it is a solid here, and you are heating it. So this is all being heated up. So when this is heated up, what happens? KClO3 begins to decompose to KCl, and it begins to give you KCl, which is also solid, and it releases oxygen gas. So here is 2, to 6, this is 3, and this is 2. Okay, balancing is very important. Now this gas goes from this tube, all the way from this tube, up into this container, an inverted test tube. And when that happens, the water begins to leave. It pushes the gases, you've seen it, the carbon dioxide, the hydrogen gas that you collected pushed the water down, right? So when this water is pushed down, the upper part gets, the gases begin to collect on the top. So let us say this gas is coming from here, all the way here, it goes here. But keep this in mind that since it's pushing, so this begins to push. So water level, I'm going to just put here, water level goes down when oxygen gas is bubbled or is collected. You will see bubbling, obviously, is collected in inverted container. Inverted, in this case it's a test tube. Okay, but it could be anything else also. Okay, so here the only thing is the oxygen gas pushes the water but becomes wet. Okay, so there is some water vapor attached to this gas we collect. And so we have to factor that in. Remember that water vapor, water in vaporized form is what? It's a gas. In vaporized form is actually a gas. So that will exert its own partial pressure. So the gas oxygen is exerting its pressure, but it's mixed with water vapor. So the water vapors will also have a partial pressure. Now, in your book, there is a table, and it was in the lab table also. So this table is table 9.2. Table 9.2 is the table of temperatures and the pressures. And the pressure given is in torr, and the temperature given is in degree Celsius. Okay, so that is why it's very important to have a thermometer here. So we know, at what temperature. This thermometer reading, you guys already took that, you guys know it. So this thermometer reading at what temperature? So let's look at this now, the situation with the learning check 9.16. Okay, learning check. Okay, here a sample of oxygen collected over water at a temperature of 29. So temperature given is 29.0 degrees Celsius plus, right, just do it here only, 273. So this is going to give you 9, 10, 11, 12, 10, 3, 302 K. Okay. Okay, a sample of oxygen collected over water. So we are looking at oxygen gas over water. Okay, at a temperature of 29 and a pressure. So the pressure is 764 torr. Has a volume. The volume is 0.560 liters. What volume would a dry oxygen have under the same conditions of temperature and pressure? So this is what volume will the dry oxygen have? That means we have to minus the partial pressure of water vapor. What volume would the dry oxygen have under the same conditions of temperature and pressure? This volume, okay. This one is, So what volume? So we need to find, okay, 1 second. What volume will the dry oxygen have under the same conditions of temperature and pressure? So volume of oxygen, and this is the total volume. This also looks like total. So what volume? Here, the pressure will remain the same. Is that it? Under the same conditions of temperature and pressure. Okay, that's a tricky one. Give me 1 minute. Okay, so this is a little confusing as far as the wording is concerned, and I have to clarify, understand this problem more, and I'll put it, if it makes sense, I'll put it, otherwise maybe something is missing, forget it. Okay, so, next is the reaction stoichiometry. That is important. Reaction stoichiometry, reaction reaction stoichiometry is basically you've done the limiting reactants, the percentage yields, those type of things. So here you are given, this is the problem 9.17 and learning check. So you are given 2 moles of acetylene, which is C2H2, and this is reacting with 5 moles of oxygen as a gas. This is a combustion reaction giving you CO2, okay? CO2 and 2H2O. Now the question is, an acetylene tank for an oxyacetylene welding torches provides volume is 9340 liters. So this acetylene obviously is in a tank. This is in a tank, and then you need to bring in oxygen from somewhere, another tank, and then you mix them together at a very high temperature. That's all welding. Okay, so you are given the volume 9340 liters of acetylene gas at temperature is 0 degrees Celsius. Okay, and 1 atmospheric pressure. So it looks like a standard conditions. So 1 atmospheric pressure, and this is equal to 273 K. Okay, how many tanks of oxygen? How many tanks of oxygen? How many tanks of oxygen? How many tanks of oxygen each providing? So the volume, each 1 tank of oxygen provides 7.00 into 10 to the power 3 liters of oxygen. Okay, at 0 degrees Celsius and 1 atmospheric pressure will be required to burn the acetylene. So how many tanks will be required? So 1 tank is giving you 7.00 into 10 to the power 3 liters of oxygen. But here's the thing. Yes, we know that this in the past, the way we talked about when we talked about stoichiometry, this means 2 moles. This means 5 moles. But when we are talking about all these tanks and all that stuff, then it's not then it's not moles. Then it just becomes volume. So this also means 2 volumes of acetylene reacting with 5 volumes of oxygen. Okay, and this guy you will use as this equality. This becomes a conversion factor. So because we need to find the tank, so this is 1 tank of oxygen over 7.00 into 10 to the power 3 liters of oxygen. So this is your conversion factor. Okay, so that's for the 1 tank. How many tanks will be needed for? Oh wait, 1 second. And this is one second. Sorry, not this one. This can be used as a conversion factor, but 1 tank is providing this much. But these guys can be used as a conversion factors. These will be used as a conversion factors. So we need to find for oxygen. So will require to burn the acetylene. So there is 7.00 into 10 to the power 3 liters of oxygen times. We need to find how many tanks of oxygen would be equal to, would be equaling to burning the acetylene. So C2H2 that burns the C2H2. So we know that 2 volumes 2 volumes of C2H2 will burns with 5 volumes of oxygen. Okay, so do this here. 7.00 into 10 to the power 3 means 7,000 times 2 divided by 5, and you get 2800. 2800, or 7,000 times 2, no, 7,000 times 5, in some second, 7,000 times 5 divided by 2 is equal to or maybe it's let's see this. So we are given 9340 liters of acetylene and 2 volumes of acetylene C2H2, okay, C2H2, and 5 volumes needs. So in other words, 9340 liters of acetylene would need how many volumes of oxygen? So 9340 liters of acetylene would need how many volumes? C2H2 would need, so cancel this liters of acetylene and the volume, 2 volumes of acetylene. So what do you get? 9340 times 5 divided by 2. 9340 times 5 divided by 2, and you get 23350. So this is 2, 3, and 350 volumes of oxygen. Okay, next is 1 tank is giving you 1 tank of oxygen is giving you 7,000. This is equal to 7,000 liters of oxygen. Okay, so we need to find how many tanks. So yeah, that was right. 1 tank of oxygen, this would be the conversion factor, over 7,000 liters of oxygen. So for 2, 3, 3, 5, 0, right, volumes of oxygen times, and volumes is in liters, 1 tank of oxygen, 1 tank of oxygen, and this is 7,000 liters of oxygen. Okay, do this, divide 23350 divide by 7,000, and you get 3.33. Yeah, that's right. So this is 3.33 tanks of oxygen are needed. Okay, so that's the stoichiometry for this one. Volumes of the reacting gases, and we also have the last is the effusion and diffusion. Okay, for the effusion and the diffusion, let's do this. Let's just we'll just do the last pieces. This one I am not, so we did this reaction of gases. Next is volumes of the reacting gases. Okay, leave this out. Billions, feet square, all that. I mean, I don't want to get too much mathematically, you know, all that. So leave it. Leave out 9.18, because it's talking about like billions and feet cube and all that. It's just sometimes that's tricky for the students. And then the volumes of the gas as a product. Now that is a good one. So I'm going to do 9.19. And you're going to, in the effusion and diffusion, as we talked about, 9.21, and then 9.21 you're leaving out, and 9.22 also, forget it, 9.22. But so we just have 2 more to go, and let's finish those. So 9.19, okay, 9.19 is 9.19 learning check. Okay, here you are given sulfur dioxide gas. Sulfur dioxide gas is an intermediate in the preparation of sulfuric acid. What volume of sulfur dioxide at 343 degrees Celsius? Okay, so we need to find a volume of sulfur dioxide gas at 343 degrees Celsius and 1.21 pressure. So that's the temperature, and the pressure is equal to 1.21 atm, 1.21 atm. Okay, is produced by burning 1 kilogram of sulfur in excess oxygen. So here's the thing, sulfur reacting with oxygen is giving you sulfur dioxide. Okay, so but this is in 1 kilograms, 100 kilograms. And first is, so here's the strategy, you need to find the volume of sulfur dioxide. Okay, you are given the kilograms of sulfur. This is given. So first thing is find out how many grams of sulfur dioxide are you producing. Okay, so this is like a test question because it relates to the, you know, the stoichiometry in the real sense. So I'm going to just put this here. So any, you know, lots, wherever there are like lots of long, you know, calculations, I will avoid those, but you should at least know. Okay, so given, convert that to grams, and grams of sulfur dioxide, or rather not even grams, actually, get it moles, just get the moles, not even grams, moles of sulfur dioxide. Once you get the moles of sulfur dioxide, once you get the moles, then PV is equal to N or T. We need to find the volume. Volume is equal to N or T over P. So we have the pressure, we have the temperature, we know the value of R, we can find the P. So let's do this. So first thing is 1.00 kilograms of sulfur, convert that to grams. So 1000 grams over 1 kilogram, that converts the kilograms to grams, times, then next is the, in this case, it's 1-to-1 ratio. So 1 mole of sulfur is producing 1 mole of sulfur dioxide. So this comes out to be what? 1000 moles of sulfur dioxide. Okay, now we have the moles of sulfur dioxide, which is the value of, that is equal to N. N for sulfur, N for sulfur dioxide is 1000. Now V is equal to N or T over P. Okay, here we forgot to convert. Temperature is plus 273. This becomes 6. So 7, 8, 9, 10, 11, and 5 and 6. So 616 K. Okay, and so 1000 moles of sulfur dioxide times 0.08206 liter atmosphere per mole K, okay, times the temperature is 616 K over P is what? Pressure is 1.21 atm. Okay, so moles and moles cancel out, atm and atm cancel out, K and K cancel out. So now you are left with 1000 times 0.08206 times 616, divide that by 1.21. So what do you get here? What do you get, guys? Hmm. Yes, guys, what do you get? 41776. But ATM temperature, so you're given 1 gram would be equal to 1000. Oh my God, I'm rushing through this. There's something I forgot. Yes, Heath. No, you're right. You're right. I'm exhausted. I think I'm just exhausted. Oh, yes. Grams to moles. That first piece is missing. Okay, let's do this. I think I'm just tired. So, okay, so let's get that. Sorry. So 1 mole, let's just do this. So times 1 mole of sulfur dioxide over, of sulfur, sorry, sulfur is 32. 1 mole of sulfur and 32 grams of sulfur times 1 mole of sulfur dioxide over 1 mole of sulfur. So now what do you get? So 1000 times 1, whatever, divide that by 32. So that comes out 31.25. 31.25 moles of sulfur dioxide. Got it? Just check it. I'm really a little bit tired today. So this is not 1000. This is going to be 31.25. 31.25. Did you get that? Moles? Good. Thank you. Moles of, so this also is 31.25. Okay, so now 31.25 times 31.25 times 0.08206. 0.08206 times 31.25 times 616 is equal to 1579. Divide by 1.21, and that is, yeah, this is equal to 1305.5. And so the volume, this is the standard notation. Standard, and that is in liters. So scientific notation would be 1305.5. The decimal moves 1, 2, 3. So this becomes 1.30, times 10 to the power 3 liters. Okay. All right, guys. One last, there's one last piece is the Graham's law of effusion. Graham, that one is easy. Graham law of effusion, EFFUSION, effusion and diffusion. Diffusion, D, what is that? DE or DI? DIFFUSION. Okay, effusion and diffusion. Diffusion is just speed, just normal way of mixing, when the two things or the gas mixes or the gas leaves a system and spreads out. So the speed with which, basically it's not even the speed. So it's just a general concept of mixing and spreading of the gases, spreading of the gases. But effusion is the speed with which they mix. Okay, the speed with which these gases mix. So we calculate that speed. You know, that speed is also called the rate. Okay, so the rate of gas A over the rate of gas B, so it's a ratio, is equal to the molar mass of B over the molar mass of A. Okay, so let's do this simple one right here, 9.20 learning check. Okay, and so I'll just put this here. So this is going to be on the test. Okay, it's a simple question. I like it. You know, it's a simple, but a little bit math is needed in the sense that, okay, at a particular pressure and temperature, nitrogen gas effuses, E-F-F-U-S-E-S, effuses at the rate. So the rate of nitrogen gas is 79 milliliters per second. Ml is what? Ml is milliliters per second. That's the volume of the gas. Under the same conditions, at what rate will the sulfur dioxide diffuse? So we need to find the rate of sulfur dioxide. Sulfur dioxide is sulfur dioxide. Okay, so what is the rate of sulfur dioxide? So you have the rate of nitrogen gas over the rate of sulfur dioxide gas is equal to the molar mass of sulfur dioxide gas over the molar mass of the nitrogen gas. Okay, now first find the molar mass of sulfur dioxide. Sulfur, one sulfur and two oxygens. Okay, one sulfur is what? Sulfur is 32, oxygen is 16. So this becomes 32 plus 32 is equal to 64 grams per mole. Okay, that's one thing for the sulfur dioxide. And then nitrogen is 2, nitrogen, each is 14. So this is 28 grams per mole. Okay, so the rate of nitrogen gas is 79. Okay, the rate of sulfur dioxide, we have to find this, is equal to, let's plug in these numbers, square root. That's the only thing here. Okay, over the sulfur dioxide is 64 and the other one is 28 grams per mole. Grams per mole cancel out. Okay, so these are canceling out. Now, you guys tell me the under root of 64 and of 28. So 64 and under root is 8. And the other one is 28 is 28, 5.29, 5.29. Let's get that piece first here. So let's solve this first. 8 divided by 5.29. 8 divided by 5.29 is equal to 1.51. So this comes out to be 1.51. And this 1.51 is equal to 79 over our SO2, the rate. Okay, so next is just 79 divided by 1.51, and that is the rate of S2. So just my algebraic conversions. So let's do this. 79 divided by 79 divide by 1.51, and that gives you 52 point. So this is 52.31. So that's the rate. So for the book is giving you 52, which is fine. That's the closest. Okay. So that's the rate of sulfur dioxide. All right, guys. So that's just, we're doing this much. And then this is a very big chapter. And I mean, honestly, it's somebody really seems to have a lot of passion for gases here. They have like really gone into that much detail I've never seen, I'll be honest. I'm teaching at other colleges also the same course. I mean, it's not, they just do simple gas laws, a little bit of the Dalton's law, and then some gas stoichiometry, and then it just ends there. But here they have really gone into detail. So anyways, so, but this is, so know these, and this ends this chapter. So like I said, just pay attention to what we are leaving. You don't need to do these questions. These are like I said, a lot of unnecessary math. So 9.18, 21, and 22. I'll put all this up on top. Leave 9.18, 9.21, 9.22. Okay, and then what else did we do here? And then also these problems that relate to the these molecular orbital theory calculations. So that's 9.23. Where is it? 9.23. And then we are calculating the, there is a velocity also, but we are not doing this anymore. URMS. And then the non-ideal gas behavior, that is 9.24. Okay, guys, so make a note of these. You guys don't have to do these, but if you want, you can do it on your own. I'm not going to cover the questions from these type of questions on the test. All right. Okay, guys, any questions? So there was a question somebody asked me, so somebody asked me about the lab. So obviously we are just now going to meet. We are now meeting only this week and next week on Tuesday. So checking out, very important, because I'm not coming on the campus after that, but we will all be meeting online Zoom as usual, right? So if you guys have, I mean, you know, it's best that you show me your work. Show me your work, okay? Show me your work and get your grades. I want to give the grades. So just make sure that you guys are, you know, this is the time. So you can come today, you can come like in tomorrow on Thursday, and then you can come the next Tuesday. That's the last. And everyone has to check out. So those things, okay? And this for and the lab today, we're just doing molecular modeling. You get full points. So no need to do any lab write-up. The only lab write-up that was needed was the labs from the previous labs. I've already shown you how to do the calculations, and I've deducted some of the stuff from the lab on, which one was that lab on the Beer's Law lab, the spectrometry lab, right? So as far as you can just show the graph of the absorption and the concentration, that's all I care. Okay, the rest of the stuff is, there's no end, you know, in science, there's no end to it. You can keep going to as much details as you want, but we need to put a stop somewhere, okay? All right, bye guys, I'll see you, bye.